Humanity is currently locked in this grand, incredibly high-stakes quest for ultimate energy efficiency. We are constantly, almost obsessively, searching for ways to power our world without, well, destroying it, pushing the absolute limits of materials science to get there. So today, we're dissecting the anatomy of an industry standard. We are looking at a material that honestly sounds like it belongs in a sci-fi movie, but is actually the cornerstone of our clean energy future: Yttria-Stabilized zirconia, or, as we'll call it, YSZ. Now, to really grasp why this material is just so incredibly important, we kind of have to zoom out and look at the massive global clean energy challenge. Because as we transition away from fossil fuels, the urgent need for highly efficient, stationary power solutions for our future grid has literally never been greater. I mean, we need systems that can generate massive amounts of electricity reliably, cleanly, and continuously. And that brings us to one of the absolute most promising technologies on the planet. Okay, let's dive into the solid oxide fuel cell, or SOFC. This is a revolutionary piece of technology. Why? Because it converts chemical energy directly into electricity without any combustion whatsoever. There's no burning, just pure electrochemical conversion. And it operates at incredibly high temperatures, like 800 to 1,000 degrees Celsius, to achieve over 80% efficiency in combined heat and power systems. But here is the catch. As brilliant as the system is, the entire thing is dangerously bottlenecked by a single central component: the electrolyte membrane. If this incredibly thin layer fails, the whole system fails. Which brings us to what we call the 800-degree dilemma, because the environment inside that fuel cell is brutally demanding. If we map out this dilemma, it reveals a massive dead zone below 700 degrees Celsius. In that zone, the ionic conductivity basically just drops to zero. The cell becomes completely useless. So we're forced to operate at extreme heats. But that heat brings terrifying operational penalties. We're talking severe thermal expansion, stressing the components, conventional seals rapidly degrading and fatiguing, and accelerated grain coarsening that significantly shortens the lifespan of the entire stack. And, well, it actually gets even more complex when we look closer at those materials. This extreme environment exposes severe structural vulnerabilities. For one, there's the constant threat of low fracture toughness. Basically, at its core, it's a brittle ceramic. So the simple act of dermal cycling from starting up and shutting down can cause microcracks, which then turn into catastrophic gas leak pathways. On top of that, we have grain boundary resistance, where impurities inside the material act like roadblocks. They literally impede the flow of ions and jack up the total internal resistance of the cell. So the crucial point we arrive at is this: we are demanding a material to be perfectly conductive to ions, completely blocking to electrons, structurally stable at 1,000 degrees, and mechanically tough enough to survive constant heating and cooling. Honestly, how do we possibly engineer any material to survive this brutal crucible of thermodynamic laws? To answer that, we have to slam zoom all the way down from the macro factory level, past the physical cracks, right down to the atomic scale. All right, Section 1, the atomic secret: forging the superhighway. The real secret here lies in something called oxygen vacancy migration. Think of this deliberate engineering like building a high-speed transit system. We are purposely creating empty parking spaces, vacancies, within the actual crystal structure of the material. And these empty spaces act as a superhighway. They allow oxygen ions to rapidly hop from one vacancy to the next, fighting that internal resistance as they migrate from the cathode over to the anode to generate power. So how do we actually do that? The chemical blueprint reveals exactly how we build that superhighway. See, pure zirconia actually expands and cracks when it cools. But if we dope it with about 8 mol% of yttrium oxide, we completely stabilize its structure. And it gets even better. To maintain electrical neutrality, when a yttrium 3+ ion replaces a zirconium 4+ ion, the lattice is literally forced to generate an oxygen vacancy. We are hacking the atomic structure to generate the very pathways that make the entire fuel cell work. But of course, having a brilliant theoretical atomic blueprint is only half the battle. We now have to figure out how to translate that sci-fi chemistry into millions of perfectly uniform, commercial-scale membranes. Which leads us to Section 2, the fabrication crucible, production force. Transforming this atomic theory into a physical reality requires a grueling, highly precise 4-step manufacturing gauntlet. First step, we assault high-purity powders through intense ball milling just to perfectly homogenize the particles. Next, we mix this into a really complex liquid slurry, coating those particles with precision solvents and binders. Third, we force this slurry through a process called tape casting, which basically rolls it out into a continuous, flexible green sheet. And finally, we lock the whole thing together in the ultimate test, high-temp sintering. And it's that final step that introduces a really dramatic manufacturing paradox. Because extreme heat is absolutely required to forge this material into its final dense state. But that exact same heat threatens to completely destroy its structural integrity. Here's why. Zirconia has incredibly slow diffusion kinetics. So forcing these loose powder particles to actually bond together and eliminate all that empty porous space requires massive thermal energy. We're talking between 1400 and 1500 degrees Celsius. The material has to go from loose particles forming small connections to locking tightly together. But here is the sintering paradox. While this brutal heat is absolutely mandatory to create a dense microstructure, just a little too much heat triggers abnormal grain growth, and that shatters the mechanical strength and drives manufacturing costs right through the roof. The stakes for getting this right are just absolute. Our target state has to be over 95% relative density. It needs to be this beautiful, continuous matrix that allows pure oxygen conduction while perfectly separating the volatile fuel gases. But the defective state? If sintering fails and high porosity remains, those open pores become fatal crack initiation sites. Gases mix, fuel is wasted in useless combustion, and the entire cell is destroyed. It's a zero margin for error process. So given how incredibly difficult YSS is to operate and manufacture, you might be wondering, aren't there better materials out there? Let's pit our reigning champion against the top ceramic contenders vying for its crown. Section 3. The Electrolyte Showdown. Contenders for the crown. If we look at the competitive landscape, it's pretty fierce. We've got GDC, which is great because it operates at much lower, friendlier temperatures and has high conductivity. But its chemical stability is incredibly poor. It actually leaks electrons. Then there's LSGM, which also boasts high conductivity but really suffers from poor electrode reactions. And then we have Yttria-Stabilized Zirconia, or SCSC. Now, on paper, SCSC looks like a total godsend. It operates at lower temps, has the absolute highest ionic conductivity of the bunch, and excellent chemical stability. But SCSSJ has a fatal flaw. While YSSJ boasts moderate, highly scalable material costs, SCSSJ relies on scandium. And scandium is one of the rarest and most expensive elements on Earth. Relying on it is literally the equivalent of designing a city's public transit system using exclusively solid gold Ferraris. Sure, it performs beautifully in a lab, but its astronomical expense completely destroys its commercial viability for a global energy grid. Which brings us right back to why YSS successfully defends its crown. It doesn't win by being perfect in every single category. No, SESZ wins on pure performance, and GDC wins on temperature flexibility. But YSS is the only material sitting squarely in the center of it all. It's a flawless compromise. It balances reliable electrochemical performance with exceptional chemical stability, and most importantly, it has decades of proven, economically feasible manufacturing pathways. Knowing this, the industry has experienced this massive paradigm shift. We aren't trying to throw YSS away anymore. We are relentlessly engineering around its limitations. We are hunting for the holy grail of next-generation power. Section 4. The Holy Grail, Next-Gen Revolution. So, to bypass YSC's physical limitations, engineers are deploying some truly cutting-edge interventions. First, they're pushing tape casting to its absolute limits to create ultra-thin membranes. This physically shortens the distance ions have to travel, which naturally lowers resistance. Second, they're exploring advanced densification techniques, like spark plasma sintering, to achieve perfect density at much lower manufacturing temperatures. And third, they are designing these ingenious composite, multi-layered sandwiches that blend the rock-solid stability of YSC with the high conductivity of materials like GDC. And all of these advanced processing techniques point to a single, triumphant payoff: dropping the operating temperature. By shifting from the legacy paradigm of 1,000 degrees down to the 600 to 800 degree threshold, we unlock cheaper interconnect materials. We finally solve the nightmare of seal degradation, and we exponentially extend the lifespan of the entire power stack. It accelerates the entire commercialization of distributed power generation. It really is a testament to the power of relentless iteration, because despite all of its incredible engineering challenges, its underlying brittleness, and its extreme heat demands, Yttria-Stabilized Zirconia remains the undisputed foundation of sustainable stationary energy conversion. Its flawless balance of properties makes it the pristine standard.
And I think this perfectly summarizes the core philosophy driving modern material science in this field today. The goal is no longer to replace YSZ, but to engineer around its flaws.
We've seen how hacking the atomic structure of a ceramic can create literal superhighways for energy, and how brutal industrial crucibles forge that chemistry into reality. But as we push the absolute boundaries of ultra-thin manufacturing and advanced composites, we have to ask ourselves, will this relentless optimization finally perfect the world's most stubborn ceramic? Or will the incredible demands of a clean energy grid eventually force us to discover an entirely new material altogether? Until next time, keep questioning, keep learning, and thanks for joining me on this explainer.